So what is the talk about? Yeah, so let me explain the title. The main character throughout this talk will be log Calabi-Yau surfaces with net maximal boundary XD. And I'm going to shorten this long sentence by just calling them net Looijenga pairs. So here, X is a smooth complex projective surface, and D is an effective reduced divisor, which throughout the talk will always be anticanonical. Simple normal crossing with irreducible components that are required to be smooth and net. The two main messages, so that's the character. The two main messages of the talk is that there are 5 classes of enumerative invariants that can be built out this data X and D. And a priori, these enumerative invariants have nothing to do with each other. They live in geometries of different dimension. They're constructed quite differently, but remarkably, they turn out to be equivalent. So there are 5 angles to look at somehow the geometry of X and D. And the second message is that all these enumerative theories are closed form solvable. So there are explicit closed forms for these invariants in all 5 cases. And this joint work with people presumably in the audience, Pierre Bousseau at ETH Zurich and Shalvangarel at Warwick. So the sort of plan of the talk and the 5 guys I was talking about will be, I will be introducing the Gromov Witten theory of the pair XD. And we relate it to the ordinary Gromov Witten theory of some higher dimensional Calabi-Yau spaces, so the local theory of X induced by D. And some of, I will propose some new correspondences relating log Gromov Witten theory to open Gromov Witten theory in higher genera. And this will mediate a bunch of connections to other classes of invariants, in particular quiver Donaldson-Thomas theory and various types of BPS invariants. Yeah, and I'll try to describe everything from the ground up. So I'm going to be mindful that there will be a problem session and this is attended by students. So hopefully this will be self-contained. So let's start. Two sorts of, one fundamental activity in science and in maths and geometry in particular is making catalogs of stuff. And in a sense, day 1 and day 2 of this workshop have seen 2 instances of this. Well, the subtitle of day 1 was classification. And so we want to classify geometric spaces and tell them apart based on their properties. And another ways of making inventories of stuff is to enumerate geometric configurations subject to certain properties. So one fundamental subset of questions in geometry are enumerative problems, and apparently that's the subtitle of today. And these sorts of questions have a history going back a long time to classical antiquity, the Apollonius problem, and some of our favorite questions fit into this subset. For example, well, the 27 lines on a smooth cubic surface, or example questions are how many rational degree D curves in the plane pass through 3D minus 1 points in general position, or for example, how many degree D curves of given genus exist on a quintic threefold, like Clem's conjecture. No, the relevance is intrinsic in enumerative geometry, but these numbers are actually relevant in many other domains of mathematics, and they pop up somewhat unexpectedly in other areas of maths and mathematical physics. And the second half of the talk, so this connection with other fields will be very much at the heart of the second half of my talk. Well, typical setup, if you want to count curves, is you have X and some algebraic variety over C. for example, the complex plane. And you want to consider some moduli space of curves in X. So thinking about the second question in the previous slide, you can consider the space of plane conics. And out of this moduli space, you would like to cook up some numbers by doing intersection theory, so-called quantum invariants. And well, the classes that appear in this intersection theoretic problem will represent incidence condition in the counting problem that is being considered. For example, conics through 5 points, leading to an interval equal to 1. Now, in general, this doesn't make any sense. This modular space is typically not non-compact, and different compactifications give different invariants with slightly different flavor that can nevertheless be related to each other. And for most of the time today, my moduli space will be the moduli space of stable maps to X. So this is moduli space of maps from pointed projective curves into X, a projective algebraic variety of given genus and degree, up to bihomomorphic equivalence. And the sort of compactification that takes place in this story is to consider not just smooth curves, but nodal curves as well, plus a stability condition. And this moduli space is a proper Deligne-Mumford stack with expected dimension equal to the dimension of the target variety X minus 3 times 1 minus the genus of the source curve minus the intersection of the class of the image of the curve with the canonical class plus n. And this moduli is a perfect structure here in the virtual class in the expected dimension. And the desired quantum invariants that you can extract out of this are computed by, well, if you single out n closed subvarieties in X, the count of degree D genus G curves through these subvarieties will be given by a suitable cap of pullbacks of the classes of these BIs against the virtual fundamental class. For example, the case of the plane, if you want to count rational degree D plane curves through 3D minus 1 points, you can compute this number ND as the Gromov Witten invariance of P2 in genus 0 and degree D through 3D minus 1 point. So pulling back 3D minus 1 point conditions on the moduli space. And well, the first few entries, you can make a table of these. Entries in the table are familiar. We have one line through 2 points in the plane in generic position. We have one conic through 5 points in the plane in generic position. There are 12 rational cubics through 8 points in the plane, essentially from basically the zoo-type arguments. And this number, two things that I want to say about these numbers is that, well, first of all, this computation is hard, and classical methods stopped in the early 80s to degree 5 until we found, well, a full recursive formula was found for the higher degrees. The second thing is that they don't ring a bell immediately. If someone popped up showing you a sequence of these numbers, that it would be hard to recognize what sort of next numbers would be in the list for degree 7. And well, the third thing is that they grow really fast and they grow factorially. As a matter of fact, there are like sharp asymptotic estimates on the growth of these numbers. So they grow like 3D minus 1 factorial times an exponential. So the base of the exponential is still unknown. And if you wanted, like I said, there is a nonlinear recursion, which is essentially the statement, well, the output of the WDBV equation for this case. And the fact that this recursion is nonlinear means that if you package all these invariants in generating function form, well, the Gromov Witten potential will be the Borel transform of this generating function. It will be convergent with radius of convergence 1 over x0. And this is a solution of a nonlinear PDE, which is quite remarkable, a solution of a particular instance of the Pinlet-6 equation. So there's quite a lot of structure in these numbers, and this should be contrasted with what I'm going to say in a minute, where I'm going to add on the geometric side an extra layer of complexity by considering quantum invariants not of X alone, but of pairs X and D. I'm going to call them smoothness pairs, where, again, X is a smooth complex projective variety of dimension M. And as in the first slide, D is an anticanonical divisor with normal crossing singularities, which each irreducible component smooth and nef. So simple examples are, you can take X, the complex projective line, and D just the 0 and infinity. Or you can take X to be the plane, and D can be, well, a smooth cubic. In this case, you have a single irreducible component, L equals 1. You can take D to be given by the union of a conic and the line not tangent to it. In this case, L is equal to 2, and both components are rational curves. Or you can take L equals to 3, and in this case, D is just a toric boundary of P2, just the sum of the coordinate hyperplanes. A piece of jargon here is that I will call a smoothness pair toric if X is a toric variety and D is a toric boundary. So the complement of D is the big torus orbit in X. I'm going to call it Looijenga, or which again is short for log Calabi-Yau surface with maximal boundary, if X is a surface and D is singular. And remember that I require each irreducible component to be smooth. So in particular, this imposes the number of irreducible components to be greater than 1. And I will call an F Looijenga pair tame if either the number of irreducible components is greater than 2, or each of them has positive self-intersection. And the relevance of this condition will be relevant in a moment. So in the previous examples, I'm just going to go back. Example 1 is toric. Example 3 is also toric, and it's also Looijenga. Example 2 is Looijenga but not toric, and example 1 is neither. And it turns out that if you impose that each irreducible component is nef, you're imposing strong constraints on how you distribute the anticanonical degree on each component. And this leads to a finite catalog of essentially 21 examples of nef Looijenga pairs, 12 of which are tame, and with a 6 more that carry essentially the same enumerative information of some tame cases. So there are generally only 3 examples that are wild in some sense. Good. I would like to attach enumerative invariants to X a nef Looijenga pair, and I'm going to use D to define, well, 2 very different in flavor geometric problems. So in the first instance, I would like to use D to define an embedding of X into some non-compact higher dimensional Calabi-Yau variety by taking the total space of the direct sum of the dual line bundles to each of the irreducible components Di. And because their sum is anticanonical, this total space is a Calabi-Yau 2 plus L fold. as a rank L bundle on X. And ideally, I would like to compute curve counting invariants, counting degree D rational curves in this total space, subject to L-1 point conditions on the zero section, the surface. Now, the moduli space of stable maps to this total space as a scheme, at least insofar as the image of the stable map intersects each component of DI non-trivially, is the same thing as the moduli space of stable maps to the base. Because by Neffness, the non-existence of sections for this bundle will impede our stable map to the form holomorphically of the zero section. So literally, we're just, as a scheme, we're just looking at maps to X, and there are no extra deformations. But the natural obstruction theories differ, and this is encoded in the fact that we have a canonical obstruction bundle on the moduli space of stable maps to X, the base, whose fiber at the smooth moduli point is the H1 of the pullback of this normal bundle to X in the target. And the virtual fundamental class for the moduli space of maps to EXD is just given by capping the usual virtual fundamental class on the moduli space of maps to X with a top chaired class of this obstruction bundle. Now, the expected dimension is the same as that of the expected dimension for the Gromov Witten theory of a Calabi-Yau 2 plus L fold. So this would be the dimension -3 plus the number of mark points. So it's L-1 plus N. And the local Gromov Witten invariants, so are sought for enumerative invariants, are computed by pulling back L-1 point conditions to this moduli space, which is a counting problem of virtual dimension 0. And there's a completely different thing that I can do with my divisor D. And instead of using it to define an embedding into a higher dimensional space, I can use it to define a boundary condition. And for example, I may want to count the number of degree D rational curves in X through L-1 points that have maximal contact order equal to the intersection multiplicity at each of the DI. And now, unlike the previous case where there was no issue with properness, here we immediately run into a problem of trying to find a compact moduli space. The reason being that having a sequence of stable maps with fixed contact orders at the DIs can have a limiting stable maps where some of the components of the curve fall entirely into the divisor. So at which point the tangency condition doesn't make any sense anymore. And this creates a lot of technical problems using traditional methods. And one way to overcome them is to use log geometry. So we can use X as a log scheme with the divisorial log structure given by D. And at that point, the moduli of basic log stable maps to X and D is a proper Deligne-Mumford stack. And this essentially, we're solving the problem of properness by coming to terms with the fact that some components will fall into the divisor by remembering the contact orders in terms of some homomorphism of goat sheaves. And if X is log smooth, which is always the case for us, it will have expected dimension equal coincidentally to exactly the same of the previous slide, L-1 plus N. So again, L is the number of components and N is the number of mark points. And again, if X is log smooth, there's a virtual fundamental class in expected dimension, and log Gromov Witten invariants of the pair XD which should give enumerative meaning to this expression in quotation mark at the beginning of the slide, are again computed by caps of point conditions, again, this virtual fundamental class. For example, my running example throughout this talk will be the plane with a line at the conic as a two reducible components for D. And we can compute these numbers, and one of the outputs of this talk will be to give a closed formula to this calculation. And two things that spring to attention immediately when comparing with the usual count of rational occurs in P2 is that these numbers grow a lot more slowly. So the growth is only exponential, 4 to the D. As a matter of fact, unlike the case of MD, where it was near impossible to find a closed form for this invariance, for this sequence, this is just, these are just essentially Catalan numbers. The binomial 2D choose D. And I will prove this later in the talk. And the second thing that's worthy of attention is if one computed the local invariance, again, there's some kind of pattern there. So this ratio grows essentially quadratically. And the growth is something like, there's an alternating sign, minus 1D times 2D squared. So if you divide by 2, you have like 1, 4, 9, 16. That's a lot more recognizable. So you can start to see a little bit more light in these examples, at least from the point of, giving meaning to generating functions. And if you consider the other example of P2 with 3 component, in this case, again, the structure of the invariance simplifies even more. So you can see that the invariants here grow quadratically. And as a matter of fact, they're actually just a quadratic power law, D squared. And if one computed the log invariance and computed ratios of the log versus local invariance, there will be again a power law where instead of having a quadratic growth, we would have a cubic growth. And if one tried to do the same thing with a smooth cubic, one would find a linear growth. So the growth is experimentally something like D to the L. And this was noticed in examples by Takahashi and then Graeber Hassett, and around 2016, 17, people started and thought that this could be actually some universal phenomenon. So despite being so different, the relative/local invariants, relative/log invariants are related by some sort of universal law to the local invariants. And they're actually the same up to a factor given by the product of the intersection multiplicities times some signed factor. So that's a conjecture for a smooth F pair in any dimension. We're not talking necessarily about surfaces. Why would we believe this other than just from looking at tables? Well, the first piece of evidence is that the conjecture is a theorem when the divisor is smooth. So the case L equals 1, proven by Van Gorel, Graeber, and Rudot in their paper where they formulated the conjecture 3 years ago. A second class of examples is given by when imposing some positivity condition on D. So when D is a hyperplane section, Navid Nabiju and Dhruv Ranganathan approved the local correspondence. And for toric pairs and possibly dropping the requirement of smoothness on X and D, we have a short paper last year, which is what actually started it actually gave us the motivation to look at the Looijenga pair more in detail. So this feels like it can be true. And the first thing that I want to say today is that this is true for Neff Looijenga pairs. So for log Calabi-Yau surfaces with maximal boundary. And we actually proved something more. So log and local Witten theory in genus 0 with point insertions of net Looijenga pairs is actually closed form solvable. So there are explicit formulas for the invariants. And as a corollary, the local correspondence can be seen to hold. And the strategy behind this, well, on the local side, this essentially borrows from two of the main solves of C3G. On the local side, the main idea is that the Gromov Witten theory of the total space can be reconstructed from the Gromov Witten theory of the zero section X through ideas going back to Kuntsevich and Giventhal in the mid-90s, and then formalized in Tom's thesis in 2001. So the basic set of steps here is that local mirror theorems compute the J function, so G equals 0, 1 point invariance of the total space from the J function of X. So the J function that appeared in, briefly in our talk yesterday. So the J function of X, so this was proposed in some embryonic form by Giventhal, and then a full treatment was given by Alessio, Tom, Hiroshi, and Chanhua in 2007. And so the point boils down to computing in closed form the J function of X, and this can always be done for net Looijenga pairs by degenerating to a toric model plus using some standard toric mirror symmetry statements. So the result of that is that the J function can be computed up to some mirror map, which turns out to be algebraic, and as a matter of fact, closed form invertible by rational functions. So this leads to a closed form expression for the invariance of the total space in terms of generalized hypergeometric series. Now, the relevance of tameness in this context, so I just recall that tame meant that D has more than two reducible components, or each reducible component has positive self-intersection, is reflected in the fact that for these cases, and precisely for these cases, the mirror map is trivial. And this would solve the calculation of invariance for only 1 point. Multi-point invariance can be reconstructed by some result allowing to derive the big J function from the small one and using WDVB. So that's a rather technical slide. In case you're not familiar with these methods, the message of this is, well, there's an explicit formula for the local invariance. As far as the log side goes, there are two main ideas, and we can split two cases. The case with two components and the tame case. It gives all net Looijenga pairs. And the two component case can be analyzed using the Abramowitz-Chen Gross-Sieber decomposition formula applied to a suitable semi-stable modification of the deformation of the normal cone of the inside X. And there's a vanishing theorem that allows to pin down exactly one type of contributions in the formula. And this is seen to give exactly the local result with a predicted factor by Van Grael, Graeber, Rudot. And in the tame setting, we can do a different calculation, which boils down to the fact that for toric pairs, Gromov Witten invariance can be expressed in terms of tropical counts in the tropicalization of X and D. So we're basically counting tropical curves in the fan of X. And most of our cases are non-toric, but there's a way using the birational invariance of Gromov Witten invariance to reduce the calculation of the log invariance of X and D to those of a toric pair. And this can be codified algorithmically in the fact that we can construct scattering diagrams for all net Looijenga pairs. And the statement of tameness here is that we have finite scattering allowing to give, again, explicit closed formulas for all the invariants. So again, the full zero log Gromov Witten theory of net Looijenga pairs can be solved. And again, if this is slightly technical, the bottom line being that there is an explicit formula and it matches the previous calculation on the local side with the expected prefactor of Vangarel-Graeber root dot. I haven't tracked the chat, so I don't know if there are any questions at this stage.
It's all good.
Okay, so I'm gonna shift gears a little bit now. So the story was all in genus 0. So at some point I was being careful to specify that I was only looking at counts of rational curves in all these various settings. But it turns out we can do better, at least on the log side. And it makes sense to consider, well, logarithmic invariants arising from moduli spaces in higher genus. Now, the expected dimension of the moduli space of log stable maps to X and D in higher genus grows by, is higher by, I would say, G than the one in genus 0. So we can compensate for the fact that the dimension of this virtual count goes up by introducing extra incidence conditions. That will be one way. And there's another meaningful operation that can be done, which is capping, still considering L point conditions on the surface, and capping everything by lambda G. So lambda G is Mumford lambda class, the G Chern class of the Hodge bundle on the moduli space. And we can pack together the invariants that we compute in this way into some generating function with a formal parameter given by the logarithm of Q. This will actually turn out to be a rational function of Q to the half. And one of the main positive aspects of doing this operation is that the scattering calculation of the genus 0 invariants translates near verbatim into a quantized scattering calculation of this generating function. So we can bootstrap the same method employed to compute genus 0 Gromov Witten invariants, log Gromov Witten invariants, to compute all genus generating functions, once again in closed forms. So there's a whole list of higher genus invariants that are relevant under many fronts that can be computed in closed form. And since they're there, one naive question one can ask is there any similar sort of refinement or higher genus version of the local invariants such that a refined or higher genus version of the Vangarel-Graeber root dot log local principle applies? And this question doesn't even make sense at face value if the number of components is greater than 1. The reason is, so ideally we look for higher genus local invariants of an F Looijenga pair XD, but the expected dimension gets lower as the genus increases in this setting, and it's negative as soon as G is greater than 1. So there's not even a moduli space to start playing with. And so this created some headache and, well, tension between the log and local word and in this collaboration. And the way out that was found is the following proposal, which is occupies the rest of my talk, is that Gromov Witten invariants of local Calabi-Yau n-folds should really be thought of as open Gromov Witten invariants of toric branes inside local Calabi-Yau threefolds. And yeah, so first thing I should do is telling you what these toric pairs are about. So there are open geometries. They are in some sense dual to the local setup. And these are the guys that have a natural higher genus counterpart to the logarithmic invariants. So what sort of Gromov Witten counting would we be looking at? So let's consider for simplicity the case in which our Calabi-Yau threefold is C3, and there's a myriad different ways of exhibiting affine space as a completely integrable Hamiltonian system, and a famous one is the Harvey-Lawson fibration. So where the moment maps is given by, well, the two differences of absolute squares of absolute values, square root of modulus of affine coordinates, and the image of the product of them three. Now, the generic fiber of the moment map is a two torus times a circle. So there's generically, clearly an effective two torus action, well, free two torus action given by scaling the argument of Z1 and shifting the argument of Z2, and doing the same for Z3 in a way that compensates these two. So Z1 goes to e to the I theta 1, Z2 goes to e to the I theta 2, and Z3 goes to e to the minus I theta 1 minus I theta 2. And this action is concentrated on the fibers, and that would explain the T2 factor. And taking the quotient by this action leaves out a real line parametrized by the real part of Z1, Z2, Z3. So that's what happens for the generic fiber, but there are special fibers given by two of the affine coordinates coinciding and being equal to 0, where this torus fibration, one of the circles in this T2 times R fibration shrinks to 0 size, giving two copies actually of an R2 times S1. And I will be considering specifically the special Lagrangian submanifolds of C3, which were considered by Lagrangians and Vafa in the beginning of the notice. Now, if instead of having C3, you have a general toric variety, which admits a presentation as a symplectic quotient, which algebro-geometrically means that the affinization morphism is projective. This picture is generalized as follows. So in the case of C3, we had the special fibers occurring in codimension 2. So the discriminant locus of the fibration was essentially a trivalent graph with a single vertex in R3. If we have a general toric Calabi-Yau threefold, which is semi-projective, the critical value set will be given by some embedded trivalent graph in R3. And a Harvey-Lawson brane, again, will be a fiber over a point on this discriminant locus. And we can isotope this picture a little to a planar partially oriented graph, so with an orientation on the non-compact edges. And we can, so this way, losing the three-dimensional perspective, we lose information about the fibration, but we can keep track of that by requiring that the tangent vectors to the edges of the graphs are actually points in a lattice. And they would basically parameterize the S1 that gets contracted on that point. Once again, having a Harvey-Lawson brane would give a marking to one of the non-compact edges. And one of the ways in which this is actually equivalent to recovering the full toric data defining Y is that this planar lattice graph is the dual graph to a height one slice of the fan of Y. So since Y is a threefold, it will have a three-dimensional fan. And since it's Calabi-Yau, the tip of the rays will lie on an affine hyperplane, so that the fan will be a cone over some convex lattice polygon. And this lattice polygon is the dual of the lattice graph describing the Harvey-Lawson fibration. So the notion of having a Harvey-Lawson brane will be given by a marking of one of the edges. There are several approaches to define open Gromov Witten invariants of an Lagrangian-Vafa brane inside X in multiple class parameterized by winding or set of winding numbers around the connected components of the boundary of the curve and its absolute homology class. Algebra geometrically, this is a hard problem for two reasons. One problem is that, that this should have been a Y, is that Y is non-compact, L is non-compact, and moreover, L has a half integer complex dimension. So L is a three-dimensional special Lagrangian. But there are various ways to define invariants, essentially by relating them to relative Gromov Witten theory in some partial compactification of Y. And this was advocated by Jun Lee in collaborations with Song and Kevin Liu, Melissa Liu, and Jin Zhou. And the upshot of that is that one can define a moduli space of open stable maps to Y with boundaries in L and fixed relative homology class, which has expected dimension 0 for all genera. And as a result, open Gromov Witten invariants can be computed again by caps, well, in this case of just 1, against the virtual fundamental class. And one can construct a generating function of those, and with the open mimicking what happens in the log case. So the way the correspondence works is as follows. Well, so our proposal is that given a Looijenga pair, we can construct a semi-projective Lagrangian-Vafa pair by taking the total space. So we take away the first L-1 irreducible components of D from X, and on this complement we take the total space of O minus DL, so the last component, which since again D is anticanonical, it's just the total space of the canonical bundle on this quasi-projective variety. So the Harvey-Lawson branes will be incident to some non-compact torus 1 orbit intersecting DI. And there's a way to identify canonically homology classes in X with relative homology classes in YL. And I'm actually going to show a cartoon now how this goes. So again, in the running example of the plane with the line and the conic. So first of all, we delete L from P2. So what we get at the level of the fan is we go from the fan of P2 to the fan of A2. And on the complement of the line, we take O minus the conic, so O minus 2 on this complement, which is just O minus 2 on A2. It's just a trivial bundle. That's just C3. So the fan of C3 is a cone over, it's just a single cone over this picture, not dash 1, just a solid one. If we had taken the canonical bundle on P2 without removing L, we would have had a cone over this this polytope with 3 smooth cones corresponding to the 3 smooth patches. Now, the Harvey-Lawson fibration. So in this case, the Y is just C3, and the Harvey-Lawson brane lives on one of the 2 non-compact torus orbits that are in the direction of the cones that we have deleted. And which one we choose is entirely immaterial for the computation of invariants, modulo some subtleties that I won't discuss. So for a Looijenga pair, we can attach a pair given by a toric Calabi-Yau threefold with an Lagrangian-Vafa brane. And we propose the following refinement of the log local correspondence, which is called the higher genus log open correspondence. And this says that for an Looijenga pair, the generating function of higher genus log Gromov Witten invariants with lambda insertion is given by a refinement of essentially a Q deformation of the prefactor in the log local case times the open generating function under this identification of the degrees. So in here, all this expressions with square brackets and subscript Q denote Q analogs of an integer n. And the one thing that I'm going to say before I justify is that it's worth believing this because it's true, at least for tame Looijenga pairs. Okay, is any question in the chat? I can't see really.
All good, but if anyone wants to ask a question now.
Okay. Okay, where does this come from? So I don't know if you've sat through talks of Richard Thomas on Vafa-Witten invariants. About halfway through the talk, there's some inevitable moment where he recalls how Vafa and Witten computed the monopole branch contribution to the Vafa-Witten invariance, which is some strange modular form. That takes like a huge paper with Tanaka to prove, and the way Vafa and Witten prove it is using two words, cosmic strings. So again, the motivation here comes from physics, and the physicist would solve this conjecture using two words, and that's my cosmic strings moment in this talk. And the two words are QFT engineering. That's where the motivation comes from. And it's, so there's a fairly influential conjecture slash theorem that in the case of local Calabi-Yau threefolds, the generating function of genus 0 and also higher genus Gromov Witten invariants should coincide with a partition function, a generating function of coming from instanton counting on R4 or R4 times S1. Going back to a proposal of Katz, Klemm, and Vafa, and then later refined eventually in papers by Goetsch, Nakajima, and Yoshoka. So Gromov Witten potentials are sometimes related to terms in effective actions of actual quantum field theories in 4-dimension, or 4-dimension times a circle by type 2A M-theory compactification on them. One could try to go 1 dimension up in the compactification and try to ask what happens in terms of the effective terms computed by taking type 2A or M-theory compactification on a local Calabi-Yau 4-fold. So in this case, the effective theory is some 2-dimensional quantum field theory with n equals 2 to supersymmetry, or in case of M-theory compactification, it's an n equals 2 theory on R2 times S1. And what the Gromov Witten potential, the genus 0 Gromov Witten potential computes for the local Calabi-Yau 4-fold is some effective superpotential term in this quantum field theory. And there is, however, an alternative way of computing the superpotential terms, which is by considering D-brane setups in a local 3-fold. So one could take a 3-fold with a Lagrangian and consider D4 branes wrapped on the Lagrangian with 2-dimensional extending. And in that case, the disk Gromov Witten potential for that Lagrangian submanifold would compute exactly the same superpotential terms. So after in 2-dimensional field theories or 3-dimensional field theories on a circle can pop up in different ways. And in some cases, they can pop up in both ways. This was proposed by Meyer in the late 90s. And in some cases, genus 0 local invariants of toric Calabi-Yau 4-fold are the same thing as holomorphic discounts on a toric Calabi-Yau 3-fold with certain Aganagich-Vafa brane. And our proposal is that this should be true for higher dimensional Calabi-Yau spaces. It should encompass more general Aganagich-Vafa brane setups. And in particular, since the higher genus set of invariants that didn't make sense for the local invariants of the 4-fold do make sense for the 3-fold, we propose that this higher genus open count refines the local correspondence. So this may or may not make the blindest bit of sense to you. And before I tell you why that's worth considering, let me tell you, after I told you what this comes from, let me tell you where this could go. So we know that mirror symmetry is special. It's good to have Calabi-Yau 3-folds around. We know that mirror symmetry is special when toric varieties are around. So it's good to have them both, like toric Calabi-Yau 3-folds. And there's a lot of structural properties that have been proved for the open theory of toric Calabi-Yau threefolds, relating them, those open Gromov Witten invariants, to other domains. One is an interpretation in terms of quantum invariance of knots via large N duality. And there's a host of all genus calculational schemes using either localization or, again, the relation with Chern-Simons and the so-called topological vertex. The generating function of these invariants are naturally partition functions of some statistical mechanical model, like random matrix models, melting crystals, or free fermions. And they satisfy very special integrable Hamiltonian equations that allow for an effective calculation of the invariants. In particular, they're tau functions for some special reduction of the two-dimensional Toda hierarchy in several cases. And the usual mirror symmetry sort of set of ideas can be generalized to higher genus by the topological recursion of a Nardor-10. And there are some fine integral structure in underlying these invariants related to their interpretation in terms of open BPS counts of like M2 branes ending on M5 branes. There's a reformulation of these open BPS counts very recently called the knots quivers correspondence in terms of Donaldson-Thomas invariants of quivers. And there are various, in keeping with the original geometric engineering idea, disgenerating functions of local Gromov Witten invariants or open Gromov Witten invariants are related to gauge theory in several dimensions. So surface operators in 4D or vortices in 2D. So I'm slightly ashamed of having put up this slide. This sounds a little bit like a used a car salesman slide, but if anybody questions your interdisciplinary credentials and at a research council, you're free to use this slide, because actually all these points are actually true and most of them are useful. So one example is if you take a net Looijenga pair given by X, the blow up of the plane at one point, you take a two-component case where one divisor is the inverse image of the line and D2 is a smooth member of the linear system given by the union of the other toric divisors, then the log Gromov Witten invariants of this pair are simultaneously related to, well, the color home flight unknown polynomial in a coloring given by the dith virtual power sum. They're the resolvent of some matrix model, the Stieltjes-Wigner matrix model, so they can be computed using orthogonal polynomials. They're a tau function of the relativistic Toda hierarchy. They can be computed using the Nardor-10 topological recursion, and they're related to a quiver partition function for a quiver with two vertices and a symmetric quiver with two vertices in one loop. So most of these points are going with friends or tell you that you have physics friends. Like I said, many of these points were actually useful in the calculations that led to the proof of the correspondence. But except for three of them, for example, point 1, 3, the integrable system, the Nardor-10 connection, and the gauge theory interpretation, I haven't found a way to tell log Gromov Witten people something that they didn't know already. But there's three of them that are directly relevant for the rest of the talk. And there's actually new theorems that we can prove through this connection. So this is the relation with a topological vertex, the refined integral structure via open BPS counts, and the reformulation in terms of quiver Donaldson-Thomas theory. So let me start by the first implication of 2 is that our motivation comes from basically reading physics papers. There's a definite recipe which deserves some better conceptual understanding. And the price that we have to pay for our ignorance is that to prove the higher genus log open correspondence, we need to prove something stronger, or at least that's what we do. And the stronger result is that the higher genus log Gromov Witten theories of tame Looijenga pairs, XD, and the open Gromov Witten theory of the associated open Gromov Witten setup, Y and L, are both closed form solvable to all general. And as a corollary, the higher genus log open correspondence holds as proposed for tame pairs. And the way the proof goes is the quintessential method of like early days of pairs symmetry. Well, you solve everything as it's stated in the statement. You solve both sides of the equality, and then you find the equality as a result. And this book actually is all about proving identities of Q series, and some of the methods were actually relevant for our proof of the correspondence. It's a great book if you're into Q hypergeometric series. And one side of the correspondence, as was advertised, is computed from the quantized scattering diagram for XD. And the calculation of the right-hand side, so the higher genus open Gromov Witten invariance of Y and L is computed via the Lagrangian Klemm-Pandharipande or the Liu-Ju topological vertex. And just as an example to maybe for people who are familiar with this type of calculation, we construct scattering diagrams systematically for all Looijenga pairs and ones with finite scattering. And in the running example of the plane with a line at the conic, the toric model is given by well, F2 relative to the toric boundary. And the way, so the Gromov Witten invariants of the pair XD are reconstructed by those of F2 relative to the toric boundary, essentially by tropical counts. And there's a focus singularity on the ray of the fan of F2 that corresponds to a fiber class divisor. So here D1 and D2 corresponds to, well, D2 is the conic and D1 is the line. And the focus singularity generates a wall, and evaluating the asymptotic monomial, say for the conic, oops, on the wall crossing function and just transporting across the wall and isolating the term of degree T to the D would extract by theorem of Mandel last year the log Gromov Witten invariance in genus 0 for this setup. In this case, it's just the binomial 2D choose D that I showed in one of the tables at the beginning of the talk. And the Q deformation just tells you that, well, the story for the quantized scattering diagram amounts to promoting all these numbers to their Q analogs. So we have a Gaussian binomial coefficient 2D choose D for the closed form for this generating function. Now, examples in higher Picard number are significantly more involved, but essentially the philosophy is the same. And well, if you've seen a topological vertex calculation in the past, again, the Harvey-Lawson setup is just C3 with one Lagrangian. And so the one leg topological vertex is just given by a Schur function in the principal stable specialization SRQ to the rho. And to extract the invariance, well, we are instructed by the topological vertex method to sum over partitions of D, taking characters of a full cycle of length D, and having some weights of the partition given by their second Casimir invariant. So by Mordagan-Nakayama rule, well, these characters are just some sign factor. The Schur function for hook representation has a simple expression in terms of binomials, and one is left with some sum over hooks. And by the Q binomial theorem, the result is, again, the Gaussian binomial coefficient that we had before with some prefactor. And this prefactor is the refined V log local open prefactor that's relevant for the correspondence. So the correspondence holds in the tame case. As a matter of fact, there are 6 twin cases of 6 non-tame cases that have a tame twin, so that extends to them as well. And I said that this has some implications. There are 2 points that are actually provides some new remarkable correspondences for log Gromov Witten theory that would have been hard to see without the connection with the local Calabi-Yau theory and its open Calabi-Yau threefold cousin. And so if for higher dimensional Calabi-Yau manifolds, there are BPS numbers, Gopa-Kumar-Vafa invariants, and in higher dimension defined in terms of, well, defined in various ways depending who you are, but in the crudest approach, they're defined by some multi-covered formula in terms of the Gromov Witten invariants. And under the log, we can think of them as coming by the log local principle from the log invariants by some multi-covering formula. And for L greater than 1, this higher dimensional Gopa-Kumar-Vafa invariants were considered exactly in this way by Klemm-Pandharipande and conjectured to be integers. A conjecture that was later proved by Ionel-Parker with symplectic methods in the compact setting. Now, what do we learn about these invariants from this web of connections with log and open Gromov Witten invariants? Well, if we consider L-1 whole open Gromov Witten open Gopa-Kumar-Vafa invariants for Calabi-Yau threefolds, we can define them by exactly the same multi-covering formula. So here, mu is the Möbius function. So it's 0 if k is an integer with repeated prime factors, and otherwise counts the numbers. It's -1 to the number of prime factors in k. It is exactly the same formula that we would have had for a Calabi-Yau 2 plus L fold. So if the genus 0 invariants are the same, then all the BPS invariants are the same. So the proof of the log local principle has already one benefit that can be reaped as follows. So since the Gromov Witten invariants are the same, the BPS invariants are the same if YL is an Lagrangian-Vafa pair corresponding to a tame Looijenga pair. And there's a surprising connection relating open Gromov Witten invariants of toric Calabi-Yau threefolds with Lagrangian-Vafa branes to Donaldson-Thomas invariants of symmetric quivers. So the first corollary of the refined log open correspondence, the higher genus log open correspondence, is that these BPS invariants of Klemm-Pandharipande are, up to a sign that I'm going to be a little vague about, the Donaldson-Thomas invariants of some symmetric quiver that can be read off, so whose adjacency matrix can be read off from the fan of X and D in a completely mechanical way. So we can use this quiver correspondence with open Gromov Witten theory as a black box, which it has appeared in different guises in the past in previous work of Pierre. In a case in which we don't impose maximal tangency on one of the divisors, we just impose extra point conditions. This is different in two ways. It's the DT invariants are not the same thing as the log invariants. They're the same thing as BPS invariants constructed out of the log invariants. So they're kind of finer integral invariants. And there's the relevance of the motivic refinement is a lot less clear in this case. So like I said, these BPS invariants are not obviously integral, but as a result of the DT invariants being so, they are integral. So the Klemm-Pandharipande conjecture for local surfaces is proved algebraically by the use of the log open correspondence in this way, essentially for free. So yeah, for example, in the running example of P2 with a line of the conic, the sort of quiver that one would have would be a 2-loop quiver. Again, just 2 loops. And in more general cases, the number of torus fixed points in Y is in bijection with the number of vertices in the quiver, and essentially the fan specifies what pattern of edges there are in the quiver. One second application is that there have been proposals to defined Donaldson-Thomas invariants for higher dimensional Calabi-Yau manifolds. Well, first from Calvin Leung in some cases, and then by Boris of Joyce in greater generality, in terms of Gieseker stable one-dimensional sheaves, and under some technical assumptions about the existence of an orientation of the moduli space, then invariants can be defined. And conjecturally, it was put forward by Kao, Malik, and Toda some 2 years ago that this invariance should be the same as the BPS invariance defined by the multi-covered formula, so the Klemm-Pandharipande invariance. And this has been checked by Kao, Malik, and Toda in examples, and a larger set of examples was considered systematically in a very nice paper this spring by Kao, Kul, and Monovari, where these invariants are computed using stable pairs. And the verification of the Kao, Malik, Toda conjecture hinges on our calculation from the log open principle of these omegas, essentially from log Gromov Witten theory or from open Gromov Witten theory. As a final application, I just mentioned passingly that higher genus log Gromov Witten invariants will be were computed by again Donaldson-Thomas invariants of a quiver, and by considering their motivic refinement. This is neither true nor expected to be true in our setting, but it still makes sense to construct BPS generating functions from these invariants, either from the log side or the open side. So from the sort of corrections that we had, other than just taking blindly Q analogs of the intersection multiplicity in the log local correspondence to get the higher genus log open, is essentially motivated by this multi-covering formula. So when we send Q equal to 1, this would go back to the first line in here, would go back to the first line in the previous slide. And conjecturally, we would expect this higher genus open BPS partition functions to be Laurent integrals. Integral Laurent polynomials, which is entirely non-obvious from the form of either the log of the open generating functions. But this turns out to be true, and we can give it, unfortunately, there's no black box that can do it for us, unlike the case for the unrefined invariants. But we can provide a direct number theoretic proof from either way, either the topological vertex or the scattering calculation. And so that's pretty much it. Final thing that I want to say, everything I said generalizes by replacing variety with Deligne-Mumford stack pretty much everywhere. And I said that there was a finite list of examples, 21 of them, in the smooth case, but playing with singularities gives an infinite list. For example, we could take X to be the weighted projective plane P11N. Instead of having a line at a conic, we can take, well, D1 to be, a line connecting one of the smooth torus fixed points with the point with mu n stackiness, and D2 to be, a smooth member of the linear system generated by the union of the other toric divisors. And in this case, the quiver would be the n+1 loop quiver. So there would be an open Gromov Witten setup, a quiver, and a bunch of all the other bonuses that we get by connecting with open Gromov Witten theory for orbitals as well. Conclusion, in varying degrees of generality for either NEF or tame Looijenga pairs as presented, the slogan is that log Gromov Witten invariants are local Gromov Witten invariants for NEF, and for tame, they're also open Gromov Witten invariants, and they coincide with, their BPS counterpart coincides with Donaldson-Thomas invariants of some quiver, and they are in turn the same as Klemm-Pandharipande, Ionel-Parker, or the open BPS invariants of Labastida-Marino-Ooguri-Vafa. And moreover, all these theories are closed form solvable. They're solved. They're not solvable in the sense of in which integrable systems are integrable. There are actually explicit closed forms for all of them.